Consider a curved graph like this. If your teacher asks you to find the slope at this location on the graph, you would visualize a tangent line at that location. If you wanted to know the slope at this location later on the graph, the tangent line would be different there. At each point on the graph, we could draw a tangent line which tells us how the graph is sloping at that particular point. And that's the thing about these curved graphs. The tangent lines are different. The slope changes. But what exactly is a tangent line, and where did it come about? Originally, tangent lines were used in the context of circles. So consider the tangent to the circle at this location. This is a pretty straightforward process, and it's an easy thing to define. We would draw a line to the back to the center, and then we would imagine a tangent line that is perpendicular to the radius. So in the context of a circle, the tangent is just the line perpendicular to the radius at a given point. At this point, there's the radius, there's a line perpendicular to the radius. Notice that these tangent lines only touch the circle at a single point. We can use this concept of circles and curvature to think about curved graphs. At every point on the graph, such as this point, there's some amount of curvature occurring. Right here, the graph is not curving very much, and so if we consider the radius of that curvature at this location, it would be a pretty big circle and a pretty large radius of curvature right here. Remember, I'm ignoring the later curvature because that's different curvature from this point under consideration. Well, once you see a circle, once you visualize the curvature via the radius, you can draw a tangent line by sending a line through that point and making sure it's 90 degrees to the radius. At this point, imagine the curvature. How tight is the radius of the curve at that location? It would be something like this. Visualize the center of the circle, the radius, and draw a tangent line at 90 degrees to the radius. So hopefully the mechanics of drawing tangent lines is starting to make sense, but what do they actually mean, and how do they connect to slope? Slope truly is a property of straight lines. It's how much the line rises divided by how much the line runs. We can calculate slope using 2 points, acquiring their coordinates, and using this formula, or we can think about it as how much the line rises divided by how much the line runs between 2 points on the line. So how do we take slope, a property of straight lines, and apply it to a curved line? For example, consider that we want to know the slope at this location. Here's one approach. We approximate the curved line as a series of straight lines. Now, I know what you're thinking. This is not going to work so well. You're right, but let's stick with the idea. Okay, so where do we want to know the slope? Oh yeah, right here. So, okay, let's take a little step to the right and then measure the slope of that straight line. This is really not a great procedure because, as you can tell, this seems shallower than what the graph is doing at this location. Well, what could we do then to our procedure to improve? You may think we should use smaller segments. Break this curve into more lines, each one being smaller, and that will improve the result. We could find this point over on this graph. There it is. We could take a small step to the right, and we could measure the slope of that straight portion. Now, you're probably thinking, okay, well, let's keep going smaller and smaller and smaller, and as those straight line segments decrease in size, our approximation will get better and better and better because we will have something that looks even closer to the actual curve. So what have we learned? we've learned if we have a curve, like this curved graph in orange here, and if we want to approximate that curve, we could draw straight lines over it. The smaller our lines, the better the approximation. So consider this point A at the kind of the bottom. We want to know what the slope is at this particular point. How do we figure it out? We break the orange curve into lots of tiny line segments. But what if the line segments were so big that the one from A reached all the way over to here? That would be terrible. This is such a huge line segment, and now we're not really approximating the curve very well. So here's what we have to do. We take this point P, and we bring it in. We make the line segment shorter. And watch what happens. As P gets closer and closer and closer, our line segment is more closely approximating the curve. And by this point, look at how close they are. Imagine that length of line covering this whole curve. It would be beautiful. It'd be such a close approximation. But we can even do better. Let's keep on going until, effectively, the 2 points are on top of each other. That's called taking a limit. And this tangent line it gives us the limit of the slope as the second point approaches the first point. So when we draw this tangent line, we are literally able to use that straight line, find its slope, and the tangent's slope tells us the slope of the orange curve at this location.